All right, good morning. I'm here. I'm running late. I planned really well this morning, but I've got kids. Does that tell you anything? I've been up since like 5:15. You know, I was ready to be here. It didn't happen that way. So, that thing out. All right, let me get this going up here, and then we'll be ready, I think. Oh, that's not what I'm looking for. There we go. I know you all have homework ready to turn in today, so what I'll ask you to do is just as you leave, we'll just turn that in on the table as we go out or over in Kingsport. I don't think anybody's in Kingsport. Yeah. Whoa, that's David. Okay.
Sorry,
hey,
I'm
David.
late. My alarm didn't go off.
Well, I just now got here myself. My daughter forgot her glasses, and I had to go back and get them. So, you know, I don't know how you forget your glasses when you have to squint without them all the time. You can't see. It doesn't make sense to me. So, I don't know. But that's what happened. So, I feel like I've been on a morning run. I don't really run, though. That's the thing. You know, I just feel like it all the time. Okay, so you all have the homework, though, due today. And just in Kingsport, I don't think anybody... Oh, there you are. Good. Just give it to David over there before you leave. And over here, you can lay it on the table as you go out. Okay? And I'll take it that way. We're going back into this section 7.4. We had barely started in that last class last Thursday. I hope y'all had a great fall break. We've been out now for a week, so that's hard to remember, I guess, when we've been out for a week, right? Out of this class, that is. So today we want to get back into that section 7.4. We still have several sections in chapter 7. I had thought we might have a test next week. I may have even said that, but I don't think we're going to be ready. So what I'm looking at now is a test on chapter 7 on Thursday, October 30th, is what I'm seeing right now, okay? So on Thursday the 30th is when we should be having our chapter 7 test. So I wanted to let you know that up front here. And keep working on the My Math Lab quizzes. Can't remember how many we have open now. 7? 7 of them, I think, are open total. So keep working on those. I think I will have an 8th one open soon. I've got an 8th one about ready there for you if it's not already. I don't think I opened it yet. I'll have to check it. We okay so far? Anybody have a question about what's going on or what we were doing for today from last week? Does anybody remember last week? Yes and no. Okay, here's what we had done. Here's what I want to talk about today. Over in section 7 for trigonometric identities. And what we had started talking about last week was we kind of reviewed the identities that we already have up here or are trying to get up here, right? All along, the ones we've been using, the reciprocal identities, the quotient identities, and the Pythagorean identities. Okay, we'd reviewed all of those. I'm going to list those back up here because we're going to be using those today as well. We also looked at the even-odd properties. Okay, so those are some other things that might come that we might need in this section. This section is not one where we get x equals 2, answers like that. It's a little bit more theoretical, I guess we could say here. Okay, so let's see what we've got. Let's go back over those identities. The basic ones here. And I think most of you already have these, but if you don't, I'm hoping if I write them enough, you know, you'll get them up here, right? So the more I write them up here, the more you see them or write them, you're going to know those. All right, so we had our reciprocal identities where the secant is equal to 1 over the cosine. The cosecant of an angle is equal to 1 over the sine, or when I put 1 over, that just means the reciprocal, okay? Those are reciprocals there. And the cotangent is equal to 1 over the tangent. Writing this theta reminds me that that last problem on your homework sheet, it should have been a theta in the equation. It was an x, and I assumed that you know that you were solving for the variable. I think it said cosine squared x. It should have been theta just because in the directions it said, you know, theta was between 0 and 2 pi. I hope that was not an issue there. Our quotient identities, we had the tangent is the sine over the cosine. All of those things we're talking about there, those thetas have to be the same. They're all the same angles. The cotangent is cosine over sine. And then we had our Pythagorean identities. Okay, so for those we had sine squared theta plus cosine squared theta equals 1. Tangent squared theta plus 1 is equal to secant squared theta. And cotangent squared theta plus 1 is equal to cosecant squared theta. Now these are the ones that we want to have in our head that we know that we can pull out and use as tools when we're working in this section 7.4. Also our even odd properties, the cosine or the secant of a negative angle, since those are even functions, will be the same as the cosine or secant of the opposite positive angle there. And the other functions we said were odd. And so they're going to work like this, to where if we have the trig function of a negative angle for one of the odd functions, then that's the same as the negative of that one. I need to rewrite this part here. Cotangent negative theta. So we've got something like this going on. Okay, these are the things we know about here. So if I recall correctly, on pages 469 and 470, we had started looking at some of these where we were simplifying. We did do an example of something there, right? Where we got a common denominator or we multiplied something out. I want to look back at one of those to start out with, okay? So maybe, I don't know, let's look down at number 15. You all were trying number 15, right? Were you trying 15 for today? Yeah, I thought so. Okay, let's look at that one. Does everybody have the identities? Okay, this is 15 on page 470. It tells us multiply and simplify. We've got the sine of theta plus cosine theta times sine theta plus cosine theta minus 1 over sine theta cosine theta. The directions are multiply and simplify. So what am I going to do first?
You would multiply the sine theta plus cosine theta by sine theta plus cosine theta.
Right, I'm going to multiply the things that are in parentheses up there. So to do that, I'm going to say sine theta times sine theta is sine squared theta. Sine theta times cosine theta will be plus sine theta cosine theta. Cosine theta times sine theta. And then there's plus cosine squared theta. And then I still have that minus 1. And the denominator I'm just keeping. Okay, nothing to do with it really right there. But now what? can I cancel? What are you saying I can cancel? I cannot cancel right now, right? I can't cancel, okay? So even though I've got that sine theta, cosine theta down below in the denominator, and I've got sine theta, cosine theta up there, whoops, on top, I can't cancel those. Why? Why can't I do that? I've got them added together, right? So when things are attached, when terms are attached with addition or subtraction, I can't break those off. That would be like, let me come down here just a minute. That would be like if I said 5 plus 2 over 5 is equal to 2. Is that true? No. See, I wouldn't even think about doing it there, but sometimes we do think about it with the trig functions and so forth. Okay, so what can we do? If we can't cancel, what are we going to do here? Okay, so you see sine squared theta plus cosine squared theta is equal to 1. We can put those together, right? Okay, let me do one thing at a time then. We'll come back and catch that then. Okay. All right, so what we now have then is 1 coming from those two. They add up to give us 1. 1 plus, what about these right here? Those are the same things, aren't they? Sine theta, cosine theta is the same as cosine theta, sine theta, is it not? Okay, so it doesn't matter which way we've got those written, but that's going to give me what when I put those together? 2 sine theta, cosine theta. And then I still have the minus 1 on the end out there. At this point, I still cannot cancel that sine theta, cosine theta that's in the denominator with anything up in the numerator because things in the numerator are being added. Now, what we did notice, though, is that we have 1 minus 1. So that's going to give me, those are going to add up to 0. So now I do just have 2 sine theta, cosine theta over sine theta, cosine theta. And now I can cancel. Okay, so the sines cancel, the cosines cancel. So our answer is just 2 here. Does anybody have a question where something went? That's usually the types of questions we see on this is, what happened to this? You know, where did that go? It disappeared. Anybody have a question on that one? Yeah, go ahead. All right, we're good on 15? All right, what was another one in that first part there, page 469, 470 that y'all wanted to see? Number 17. Okay, let's take a look at that one then, okay? $17 says to factor and simplify. Now we have 3 sine squared theta plus 4 sine theta plus 1 over sine squared theta plus 2 sine theta plus 1. Okay. This one says to factor and simplify. So the first thing we're going to do is the factoring. And both of these appear to be, you know, like they're trinomials, and we're going to factor in that manner somehow. All right, so the first terms we'll have to multiply to give us the first term. So what are we going to fill in there? Three sine theta times sine theta gives me 3 sine squared theta. And then we see the last terms will have to be 1 times 1 to get that 1 up there, right? All the signs are pluses in what I started with, the trinomial up there, so they're going to be pluses here as well. How do we check to make sure we get that 4 sine theta? Y'all remember your factoring, right? this part here and this part there, when we combine those, 3 sine theta plus sine theta gives me 4 sine theta. That's where that middle part's coming from. All right, in the denominator, I'm going to have a sine theta times a sine theta to get sine squared theta, a 1 times 1 to get the 1. All signs are plus again. It does look like I'm seeing that 2 sine theta when I do the outer and inner products there. So we've got that part done. So now what? Yeah, now we can cancel. And that leaves us then with 3 sine theta plus 1 over sine theta plus 1. Can I do anything else? Nothing else. Nothing. 3 sine theta plus 1 is different from sine theta plus 1. So that's as far as I can go. Nothing else I can do there. I cannot cancel out and make the answer 3 because I could cancel if it said this, okay? If it looked like this, to where sine theta plus 1 cancels with sine theta plus 1, I could do that. The problem up there, though, is this is 3 sine theta plus 1, and I cannot pull that 3 out. Do you see why? If it was 3 sine theta plus 3, I could pull that out, okay? It's not this, though. That's not what we have. So we cannot cancel there. Go ahead.
I just don't understand how you would pull the 2 out to number 15, but not able to pull 3 out on this one.
Okay, let's look back and see on 15. On 15, where we had 2 sine theta cosine theta, actually, let me go over here to a different page and write this. 2 sine theta cosine theta. And it was over sine theta cosine theta, right? And this other one, what's it saying? 3 sine?
Sine theta plus 1 over sine theta plus 1.
So what is the difference? Why does this one equal 2? This one has to stay that. This one's equal to 2. What's the difference?
So you got a 2 times sine theta times cosine theta up top. Whereas down here you got 3 sine theta plus 1. The 3 is part of the sine on number 17.
Okay. Okay, that's a good description. They couldn't hear you over in Kingsport there, okay? So you want to tell us again there? Thank you.
Yeah, the 2 sine theta, or the number 15 is 2 times sine theta times cosine theta. It's like 3 separate things, whereas in number 17, the 3 sine theta is just one term.
Right, in 17, the 3 sine theta is all hooked together as one term, but then the clincher is you've got plus 1 out there with it, so it makes all that go together. Up on top, on number 15, in that problem, the reason we can cancel there is they are all being multiplied. We don't have anything being added or subtracted. Okay, so it's like this. Let me put real numbers up here. 2 times 3 times 4. This would be similar to what we have in 15, right? And even if we multiply that out, we get 24 over 12, which is 2, correct? Okay, but likewise, we could do that and get our 2. Down here, we would have something like, I don't know, 3 times 2 plus 1 over 2 plus 1. Okay, that's what I'm looking at there, where I'm letting the sine theta be the same as the number 2. Okay, and everything else is staying the same. Now, the question is, you know, well, we see that this has got to be 7/3 if we really work that out. That's 7/3, right? But doing what we're kind of testing here, we would say, can we do that? And see, we don't get the same thing. See, that was incorrect. Because the 3 and the sine theta is multiplied together as one term, plus the other value, okay? Whenever you're canceling, and you're canceling things that are added and subtracted together, they have to be exactly alike. So we could cancel a 3 sine theta plus 1 only with another 3 sine theta plus 1. Does that help see it a little bit better? If everything's being multiplied, then we can take the individual parts that are creating that product. Okay, does that help? A little bit there. Anybody else have a question on this problem, or on either of these? Go ahead.
If there was no addition in 17, if it was just 3 sine theta over sine theta, could you cancel then?
Yes, if it was 3 sine theta over sine theta, then we could cancel and get 3. That works, okay?
So you couldn't cancel the ones either?
We cannot cancel those plus ones. No, we cannot. We cannot cancel the plus ones. If we could cancel plus ones, then if I have 6 plus 1 over, I don't know, 11 plus 1, I could just do that. You wouldn't even think of it there, would you? You wouldn't even think of doing that. Okay. All right. So this is kind of just showing, why we can't do this stuff on this page here. That's what we're looking at, what's legal and what's not legal in simplifying these things. Okay. As long as everything's being multiplied, we're okay. We can cancel the individual pieces there. But when we start putting in that addition or subtraction, that changes things. Okay. Good questions, though, because we'll have to think about these as we go throughout. Anything else on 15 or 17 there? Yeah. Something else. Go ahead. 11. On 11, we have multiply cosine of theta over 1 minus sine theta by, I'm just going to go ahead and make it multiplication, 1 plus sine theta over 1 plus sine theta. Here we notice that we're multiplying by 1 in disguise, right? A form of 1. Something over itself, so that's equal to 1. We don't want to just cancel, though, here, because they're trying to get us to change the format of what we first started with. Whatever we get is going to be equivalent to the cosine theta over 1 minus sine theta. So that's what we're looking at here. So what we have is cosine theta on top times 1 plus sine theta. Remember, we just multiply straight across. 1 minus sine theta times 1 plus sine theta. Okay. And what's that going to give us then here? Well, in this one, and this is probably from looking at it before, but let's leave the top part a minute and see what we get in the denominator. Because I think something on top may cancel here after we work out and see what we actually have in the denominator. What's this stuff here equal? 1 minus sine theta times 1 plus sine theta. What do you get when you multiply that out? 1 minus sine squared theta, right? Just 1 minus sine squared theta when you multiply that. So on top, I've got my cosine theta times 1 plus sine theta. In the denominator, what is 1 minus sine squared theta? That's equal to cosine squared theta, isn't it? Since cosine squared theta plus sine squared theta equals 1, then 1 minus sine squared theta must be equal to cosine squared theta. So we're using one of those identities here. Well, since we see that, we can take cosine theta, divide it into one of these cosine thetas, leaving us a cosine theta down there. And we're getting 1 plus sine theta over cosine theta. We could leave it there. The book leaves it there. But this is one of those we could take it a little further. We could say, that's 1 over cosine theta plus sine theta over cosine theta, which is equal to what? Secant theta plus tangent theta. So we could say that, right? We could break it up and say it's equal to that. So there's 2 ways we could come out here. Does anyone have a question?
You couldn't cancel out the plus sine theta on the beginning.
On the beginning, why could we not cancel out the 1 plus sine theta? If we did, we're only going to get cosine theta over 1 minus sine theta, and the directions here actually told us to multiply and simplify, so they want us to multiply, and what they're trying to show us is that that thing we started with, that cosine theta over 1 minus sine theta, is equivalent to these two circled things down here. Okay, that's what they're trying to show us there, that what we started with, could look like either of these other things. They're equal. They're all the same, because all we did was multiply what we started with by 1, right? So we were multiplying in this case just to manipulate it into looking like something else. What else there?
You have it at the end where it says secant theta plus tangent theta. I was looking at my identities. Is that Pythagorean or?
That's not a Pythagorean identity there, because it's just secant theta. It's not secant squared. It's not tangent squared.
Okay.
And those, on the Pythagorean identity, it was tangent squared theta plus 1 equals secant squared theta.
Okay.
So yeah, this one's not a Pythagorean identity. It's just secant theta plus tangent theta. Correct.
Okay. Oh. Okay.
See it there?
Yeah,
because it's 1 over the cosine and sine over the cosine. Okay. Where we split it apart. What else on this one? Anything else there? It's making us think about the identities, hopefully. That's what this is trying to do. It's making us think about the identities, get some of these operations a little bit better in our heads here. Well, let's actually look at how we're going to establish an identity, because that's ultimately what we want to do in this section, is be able to establish an identity using these identities that we have in our toolbox there, so to speak. Okay, so let's see what we can do with establishing. Now, in your textbook, you have the steps to establish an identity. We're going to put those up here, but if you want to follow along, it's on page 469 in the book. These are just guidelines for establishing an identity. That's what they say. They're just guidelines, okay? Always start with the more complicated looking side. Now, what we're doing when we establish an identity, they're telling you to start with the side that looks the toughest. What we're doing when we establish an identity is we're only going to work with one side. An identity already tells us that one side's equal to the other. We're verifying it when we establish it. We're actually kind of proving that the left side equals the right, or the right side equals the left. To do that, we're going to take one of the sides, whichever one looks the worst, I guess we could say, and we're going to manipulate it to try to turn it into the other side. We will not be working with both sides of the identities. We will only be working with one side. That's different for us because we worked with equations not too long ago. And with the equations, we know, that we add and subtract to both sides and things like that. Whatever you do to one side, you do to the other. We're not solving anything here. We're not solving equations. We are establishing identities. So the first thing is I want to just kind of clarify those differences. If we're solving an equation, we're trying to get the variable by itself. If we're establishing an identity, we're trying to turn one side into the other. Does that make sense? So we're only going to be working with one side on these. So we want to use the more complicated looking side. We want to rewrite any sums or differences as one quotient. That means if you have fractions being added or subtracted, we want to combine those by getting a least common denominator. Okay? So we're going to say here combine fractions. Next thing is rewriting everything in terms of sine and cosine could be helpful. I say might be helpful because it might not, okay? These are just guidelines, okay? Not necessarily specifics. Sometimes it's helpful to do that. Sometimes you may have to try something else. Fourth one, no matter what you're doing with this stuff, always keep your goal in mind. And your goal, what that's talking about is, remember what you're trying to get this to look like. Remember what was on the other side. I'll just say remember what you're trying to get to, okay? And I'll show you what I mean. I'm going to show you some examples here. Okay, so let's see how this is going to work out. We're going to work with one side and see what we get. Is everybody finished with the screen here? Yeah? Okay, good. So I'm over on page 470, and the first one I'm going to use is how about number 24? Let's use that one. It says the sine of theta times the cotangent of theta plus the tangent of theta equals the secant theta. Sine theta times cotangent theta plus tangent theta equals secant theta. All right, to establish the identity, what I've got to do is figure out first which side am I going to work on manipulating to turn into the other side. Which side looks the worst? The left side, right? The left side. Now, the reason we want the side that looks more complicated is because it has more things on it that we can manipulate or work with, okay? That's why there's not as much we can do with this right side here. So we're going to work on the left side here. On the left side then, what would you like to do? What does it look reasonable that we might do here?
Change the cotangent theta and tangent theta to a sine over cosine plus cosine over sine.
All right, so he says change everything into sines and cosines. So cotangent's cosine theta over sine theta plus sine theta over cosine theta. I'm not doing anything to the right side, okay? I'm just going to bring this left side down and work with it and see what I get. My ultimate goal, though, is I want it to say secant theta. I want to turn the left side into secant theta. So on the left side, what would I do now?
I would probably put a 1 underneath the sine then.
Okay, you want a 1 underneath the sine, and you said to multiply, right? Okay, that's what we're going to do. So we're multiplying here. So we've got sine theta, if you want it over 1, put it over 1, times cosine theta over sine theta, plus sine theta over 1 times sine theta cosine theta. We're distributing the sine theta to each of those. We could have done that from the start before we changed things to sines and cosines. That would have been legal also. What do we get here now? Cosine theta plus sine squared theta over cosine theta. Because those canceled there, right? Well, that does not look like secant theta. So, okay, the suggestion here is get a common denominator. See what happens then. We're always looking for things we can do. What can I do to try to make this look better? What can I do? Okay, so the suggestion is get a common denominator, which would be what? Yeah, cosine theta is the only denominator we're working with right now, so we'll put it for this one also. This first one here is cosine theta over 1 originally, so now it's going to be what over cosine theta? Cosine squared theta, good. Over cosine theta. The second one, the sine squared theta, is going to stay the same up there because we did not change that fraction. Well, that gives me then cosine squared theta plus sine squared theta over cosine theta.
How did we get cosine squared?
We're changing to an equivalent fraction. 1 times what gave me cosine theta? 1 times cosine theta, right? This has to go through the same change. So cosine theta on the top times another cosine theta is cosine squared. We're getting an equivalent fraction here, just with a different denominator. Okay? Just like if I change 1/2 into 2/4. All right? So what do we have now up here on top? I have 1 over cosine theta. What's that equal? What I want it to equal? Yeah. There they are. They're the same, right? Okay, that's what I wanted to get to. That was the object here of this little puzzle. It's a puzzle, right? We'll make it all a game. We're trying to turn one side into the other. So you don't like these games, right? You've played better games? Is that what you're telling me?
I just want to say, let's play a game. Think of Jigsaw.
Yeah. Jigsaw puzzle. No. All right. So this is a puzzle. Here, Tom, go ahead.
Whenever you add cotangent and tangent, can you just turn that into a 1?
When you add, the question is, when you add cotangent and tangent, can you turn that into 1? The deal is, and you're talking up from the very beginning, right? Cotangent theta plus tangent theta does not equal 1, but cotangent theta times tangent theta equals 1. Okay, so that's the clincher there. It was addition instead of multiplication, so just be careful. All right, what else there on this one? Do you see what we're doing with establishing? We're taking one side, we're manipulating it. That's all we're doing. We're saying this is really equal to this and this is equal to that until we get it, managed around to look like whatever's on the other side. Okay, that's what we're doing here. It's making us think. This is the thought exercise, isn't it? Problem solving here. Anything else on 24? I want to do a few more of these because they all work out a little differently. Let's go over here then to, let's try 32, see what it's doing. 1 minus cosine squared theta times 1 plus cotangent squared theta equals 1. Which side are you going to work on?
The left side.
Left side. Again, the left side looks the worst. So we're going to work on the left. What are we going to do on the left?
The 1 plus cotangent squared theta is equal to cosecant squared theta.
Okay, so I'm hearing two different proposals here. I heard multiply, and I see a Pythagorean identity there, right? So I don't know. It's your choice. You can try either one. Sometimes you try something and it works. Sometimes you try something that doesn't work. Sometimes there's more than one thing that is going to work. One might be a little longer than the other. So I kind of like that Pythagorean identity thought here. Somehow I think that's going to be a little simpler to work with. I don't know. But let's try that. I was told that 1 plus cotangent squared theta is equal to cosecant squared theta. What about 1 minus cosine squared theta?
That is equal to sine squared theta.
That is equal to sine squared theta. So now I have sine squared theta times cosecant squared theta. So what's that equal to? Sine squared theta. What's cosecant squared theta? 1 over sine squared theta. And those cancel. So that's equal to 1. So we got it there, right? That was pretty quick actually doing it that way. Now, chances are it would have come out okay if we multiplied it out, but I'm guessing it would have been a little longer to work with. If you see an identity, usually that's a good thing to use. That should be on the guidelines list. I didn't put it on there, but let's say if you see an identity, you might just want to go ahead and put that in. Okay. Are we okay on 32? Does anybody have a question on 32? Let me find us another one here. Actually, I have some already picked out for you. Let's go down to how about 42? Let's go to that one. We have 1 minus sine squared theta over 1 minus cosine theta equals negative cosine theta, right? That's what we've got there. Okay. Which side are we working with here?
Left.
Left side, good. What do you propose I do with the left side this time? What can I do with that left side? Rewrite the sine squared theta as 1 minus cosine squared theta. You think that's going to help? Maybe. We'll see. We don't know. So the suggestion is rewrite sine squared theta as 1 minus cosine squared theta. We'll go with that. See what happens. What can I do now? I've got a number minus a fraction. I need a common denominator. Yeah. Whether you like fractions or not, we got to do them. Okay. We need a common denominator here. What's my common denominator?
1 minus cosine.
It must be 1 minus cosine theta. That's the only denominator we have here. So I'm just rewriting both of these parts so it has 1 minus cosine theta. This fraction part already had that, so I don't need to change anything in there. What am I going to do to get that 1?
Just make 1 minus cosine theta over itself.
Yeah, 1 minus cosine theta over itself, because 1 is anything over itself, and we know we want that denominator to be 1 minus cosine theta, right? So we'll use that there. Now maybe we want to put it all together and just have the one denominator. Okay. So up on top, I'm just going to write it all out right now. I have 1 minus cosine theta. What else do I have now on top?
Minus 1 minus cosine squared theta.
Okay, but it's minus all that. When that whole fraction is following the minus sign, what's going to happen?
Makes it plus.
Yeah, minus 1 plus cosine squared theta. So we'd have to watch our signs there. Okay, we would have to watch those signs. Because the whole fraction is following this minus sign right here. Okay, so everything that we have after that is going to be negated from that numerator where we're combining. Okay, so we have to carry through that minus sign. What does that give us?
Gives you
All right, negative cosine theta plus cosine squared theta over 1 minus cosine theta. And the question here was what? Could I what? Got to remember my goal. My goal is to get negative cosine theta, remember. Okay, I can factor out a negative cosine theta on top. What does that leave me? Conveniently, it leaves me 1 minus cosine theta, right? So I factored out a minus cosine theta. What was I trying to get? Minus cosine theta, okay? When I'm looking at this right here, this right side there, I'm seeing they both have cosine theta. I'm trying to get negative cosine theta, so let's go ahead and just pull out negative cosine theta and see what happens. Those cancel, and I'm left with negative cosine theta. In some of these cases, there may be other ways we can do these, okay? It may not be just the one, this is the only way. Some of them might be, but this one I suspect there are other ways we can go about getting there. So not everyone may think of these same steps at the same time, but they just have to follow, the identities that we already are used to using, those standard identities. They have to follow those. You have to be able to plug those in accordingly here. Does anybody have a question on this one? In this part. I know this part's a little strange. A lot of people don't like this stuff. I'll just tell you up front, a lot of people don't like this.
What identity are we using for the cosine square theta there?
For the cosine squared theta?
Yeah, where we plug in the identity down at the bottom.
All right, here? Yeah. What we did here is we factored out a negative cosine theta. They both have cosine.
Okay.
Right there and there, both have cosine theta. So we factored out negative cosine theta because that's what we're looking for mainly, is why we use that. And then what we're saying is negative cosine theta times 1 gives me back that term up there. Negative cosine theta times minus cosine theta gives me back the plus cosine theta, squared theta.
Okay.
So we're factoring it back out is what we're doing. Pulling the factor out. Okay. It's a common factor. What else there? Any other parts that we're not sure about? Well, maybe, let's see, maybe one more example or so of this. Let's see what we've got here. Let's go over to, we'll go a little further over to 78. Try that one. So this is on 471 in your book. We have secant squared v. Now it's v instead of theta, okay? Minus tangent squared v plus tangent v over secant v equals sine v plus cosine v. Which side do you want to work with?
Left.
Left side, okay? Left side. So what are we going to do on that left side? See anything with an identity here, maybe? This one looks a lot worse, doesn't it? Looks pretty bad. But I'm seeing some squared things. That secant squared v and tangent squared v makes me think we might could use a Pythagorean identity here. But what would it be?
That would be
One plus tangent squared v equals secant squared v, right? So let's put that over here somewhere. Here's what we're going to use. 1 plus tangent squared v is equal to secant squared v. Okay. So what can we do with that? Now see, we've got secant squared v minus tangent squared v. What would that be equal to?
1.
Yeah, that's equal to 1, isn't it? So we actually have 1 plus tangent v over secant v. We're trying to get to sine v plus cosine v. Go ahead, Brent.
How did we get that equal to
Well, we're looking for, okay, we got this part here, right? And we know this over here on the right side of the screen. So what we have is if we take away tangent squared v from both of these sides, now I have 1 equals secant squared v minus tangent squared v. We're just manipulating the identity we started with. Just like where we say sine squared theta plus cosine squared theta equals 1, so 1 minus cosine squared theta equals sine squared theta. Right? We're manipulating from side to side on those things algebraically. All right, so secant squared v minus tangent squared v, are we convinced that's 1 now? Everybody okay with that? And I would rather you ask than just believe everything I say, you know? It's good to ask. All right, so what are we going to do now? Sine squared v plus cosine squared v, it could be. I don't know that we need to here. We could try it, but what? Yeah, tangent is sine v over cosine v. We're probably going to have to do that eventually because we're trying to get to sines and cosines, which was your objective with changing the 1 also, wasn't it, to get to sines and cosines. And that might work. I don't know. Let's see what we've got here then. I don't know if we want to go that route or not because I'm seeing it here. I'm seeing it. Are you all seeing it? What else can we do here? Go ahead.
Can you break it up into 2 different fractions?
That's what I'm seeing. Let's break it up. 1 over secant v plus tangent v over secant v. That's what you're telling me to do, right?
Yes.
I think that's what we want to do there is break it up because when I see 1 over secant v, I'm already seeing the cosine v part right there, right? So 1 over secant v is cosine v, but I do agree we're going to have to change this tangent and secant into sines and cosines to see what we're working with here. So I've got sine v over cosine v for tangent and 1 over cosine v for secant. So I've still got my cosine v plus this stuff over here. Yeah, you can just cancel. I'm going to write out and show what's happening here. We got sine v over cosine v. We've used that technique though before. And times the reciprocal of what's on the denominator. So we do have cosine v plus sine v. The suggestion was that from there, you know, we can cancel those. Just like when we had the radicals and we were getting the trig functions, we had the same things in those denominators. We saw that those things were canceling, and that just left us with sine v in this case. Okay. It's important to know that list of identities that we put up at the beginning of class. Do you see why? Are you seeing why it's pretty important to know those, to have those in your head? Even though, like up here where we use the 1 plus tangent squared v equals secant squared v, and then manipulated that to get the secant squared v minus tangent squared v, where we use that stuff, we did manipulate something from the original, but it's good to know that original already and have an idea of what you're working with there. Does anybody have a question on that part? I want to start just a little bit into 7.5. Y'all are going to work on some of these for me to practice with. I'll put them up here toward the end. But on 7.5, just to give you a break from the theoretical stuff, we're going to get into some formulas. Okay, and sometimes people like formulas better than the theory stuff. So let's see. 7.5 is sum and difference formulas. We're just starting in this one just a little bit, not going too far today. What the sum and difference formulas do, they allow us to find exact values. You know, we've been finding exact values a lot. When we ask for exact values, what's the exact value of the sine of pi over 4? We'd say the exact value is the square root of 2 over 2. No decimals there. What if we want, though, the exact value of something like pi 12ths, that angle? That one's not one that we put down on our unit circle, but there's a way to get that exact value through the use of adding or subtracting 2 angles that we know about. If we can add or subtract 2 angles, and come up with an angle that is not actually on the unit circle, then we can use the sum or difference formula in order to get the exact value for that trig function for that angle. So these are some formulas here. Sum and difference formulas are in your book over in section 7.5, and they've got them all listed out here for you, but let me put up here what we've got. What we're looking at here are these formulas. The sine of alpha plus beta. Alpha and beta are two angles. They should be two angles we know about. Two angles off our unit circle here. Sine of alpha plus beta will be sine alpha cosine beta plus cosine alpha sine beta. The sine of alpha minus beta, this would be the corresponding difference formula for sine. Be sine alpha cosine beta minus cosine alpha sine beta. Cosine alpha plus beta, we'll look at that one also. Cosine alpha, cosine beta, minus sine alpha, sine beta. Now that sign in the middle changed this time. If it's the cosine of alpha plus beta, then we got a minus in between these values. If we're on the sine of alpha plus beta, though, the sign in the middle stays the same. Okay, you know what I mean? The sign in the middle, what I'm talking about here. This right here stays a plus if we're doing the sine of alpha plus beta. Stays a minus if we're doing the sine of alpha minus beta. But if we're doing the cosine of alpha plus beta, we got a minus sign over here. Okay. Cosine alpha minus beta. It's the same thing as what we just had, just the sign in the middle is going to change. So we'll start out just looking at those. We have one for tangent here also. I don't know, maybe we should go ahead and put the tangent one up while we're here. Let's just go ahead and put it on here. Tangent alpha plus beta. It's going to be tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. And likewise, the tangent of alpha minus beta will be tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. Somewhere in your book they have all of these listed. Oh, over on page 481. That's a good place to see all those in the textbook. Okay, they've got them all together there. They have them spread out throughout the section also. Now, sine, cosine, tangent, those are the only formulas we get here, because if we can get these three things, then we can reciprocate and get the other three trig function values, right? If we've got these three, we're good. So let's see how these are going to work. Okay, that's what I want to show you, is just how this is going to work a little bit here. So these are all in your book on page 481. We're going to start out with one that's a sine. And in fact, we'll use the sine of pi 12, since I said that pi 12 a while ago. Okay. Now, the only problem with that might be is that pi 12 is in radians. And some of the angles we work with in this section will be in degrees, back in degrees, even though everything else we've done in this chapter so far, I believe, yeah, has been in radians, right? Everything we've done in this chapter has been in radians up to this point.
Well, we can just convert them, can't we?
I guess you can convert if you want to, yeah. I'm not going to convert today, though. Okay. Let's look at the sine of, what did I say, pi 12s. The deal with pi 12s is that it is not one that we've looked at on the unit circle. Pi 12s, you know, we've looked at pi 6, pi thirds, pi fourths, pi halves. We didn't say anything about pi 12s. Okay, but how can we get pi 12s out of some things we already know about on the unit circle? How can we do that? Let's think about some of those we do know about. Pi thirds, pi fourths, pi 6 for starters. We'll look at those. Okay, we're just thinking right now. How can I get pi 12s out of these? First thing I would want to do is see, well, what are these as 12ths? Because how am I going to somehow add or subtract two of these and get pi 12ths? That's what we're trying to do in order to use the sum and difference formulas, okay? So how can I do that? Pi over 3 is equal to what over 12?
4 over 12.
Yeah, 4 pi 12s. Pi fourths will be 3 pi 12s. And pi 6 will be, maybe I didn't even need all those. But how can I get pi 12ths out of two of those?
You can subtract pi thirds from pi fourths. Or pi fourths from pi thirds.
Okay, so say pi thirds minus pi fourths. That's one way. There's more than one way here to get it, right? We can do, what we just said was 4 pi 12ths minus 3 pi 12ths is equal to 1 pi 12th. But we're putting it back in the ones we know, pi thirds minus pi fourths. Was there a question? No, okay. We could have used pi fourths minus pi 6, couldn't we? Either way is okay. Just so you're getting, once you subtract or add, we want whatever we use, we want it to give us pi 12ths. And pi thirds minus pi fourths does give us pi 12ths. Do you all agree? Are we together so far? We're rewriting pi 12ths. That's our first step here. Question now, which formula does this look like now? Sine of, which formula, which one? Alpha minus beta. That said, let me put it down so I can put it all on one line maybe. Sine of alpha minus beta equals sine alpha cosine beta minus cosine alpha sine beta. Right? That's what we've got there. All right, so on my problem over here, then it looks like pi thirds is my alpha and pi fourths is my beta for going into that formula. See what I'm doing? You know how the formula works. We're trying to set it all up and plug in according to the formula. So now what I have here is going to be, let me bring that down a little too. I'm not leaving myself enough space. Sine alpha, meaning the first part, times cosine beta, or that second value, pi fourths, minus cosine pi thirds sine pi fourths. That's how I'm expanding it out into this formula. If I have sine of pi thirds minus pi fourths, I'm going to expand it out now into sine pi thirds cosine pi fourths minus cosine pi thirds sine pi fourths. You see how I'm plugging into the formula? Is everybody watching, seeing how that goes? Does anybody have a question so far? The deal here is that I know the sine of pi thirds and I know the cosine of pi fourths. I know these values, so I can plug in actual numerical values for these things. I know them from my unit circle, correct? I know all these. All right, we're supposed to know all these. Okay, the sine of pi thirds. What's the sine of pi thirds?
Square root of 3 over 2.
Square root of 3 over 2. It's unanimous over here. All right. Times, what's the cosine of pi fourths? Square root of 2 over 2. Minus, what's the cosine of pi thirds? It's 1/2. Good. Sine of pi fourths? Square root of 2 over 2. I wrote it to multiply. You know, we're multiplying these things because of the way it's written. All right, now I have to remember how to multiply radicals. Square root of 3 times square root of 2 is?
Square root of 6.
Square root of 6 over what? We're multiplying over 4. When you're multiplying fractions, remember you multiply the numerators and you multiply the denominators. Okay, you got to multiply both parts out. Then minus what?
Square root of 2 over 4.
Square root of 2 over 4. So it gives us square root of 6 minus square root of 2 all over 4. Can I do anything else with that? Can I do anything else with square root of 6 minus square root of 2?
I don't think so.
No, you can't. Good thinking. Okay, you cannot. Because the only way you add or subtract radicals is if they have the same radicand, the radicand being the number underneath that radical symbol. That's the only way we can actually combine those. In other words, if I have the square root of 2 plus the square root of 2, then I could say it's 2 times the square root of 2. But with one of them being a square root of 6 and one being a square root of 2, I can't do anything with that. Now, that thing right there, square root of 6 minus square root of 2 over 4, is the exact value of the sine of pi 12s. May not be worth a whole lot to us overall in real life, if we're working with something there, but we need to know how to get that exact value. Another way you might see this answer written, just so in case you see it in the textbook, sometimes they'll do this. They'll take, instead of having it over 4, they'll pull out a 1/4, have it 1/4 times this stuff. You all see that that's the same, right? Everybody see that's the same thing. 1/4 times that is the same as that stuff on top divided by 4. My feeling is that the bigger thing here is figuring out how to rewrite that angle, that pi 12s, figuring out what am I going to combine to get that value. Now, if you can do this problem right here, you could also do the cosine of pi 12s, the tangent of pi 12s, by plugging into that formula. Once you already know, how you're writing that thing right there. Okay, once you know that part, right? You've got your alpha and your beta. I think we can do one more of these. Let's do one more something here. Let's do the cosine something here, just so you'll have at least a sine and a cosine down. Let's do the cosine of 105 degrees. I'll put it in degrees this time. Again, 105 is not something we typically look at on our unit circle. Can you think of 2 angles you can use to get 105 degrees?
45.
All right, 45 and 60. And we're adding them this time. So somewhere I want to remind myself that this is the formula cosine alpha plus beta equals cosine alpha, cosine beta, minus sine alpha, sine beta. About to run out of space there. Can we see that okay? Cosine, cosine, sine, sine, and on cosines the sign in the middle is different. Okay. So what's my alpha? Right there, there's 60 degrees is my beta. So I'm going to have, this is equal to cosine 45 degrees, cosine 60 degrees, minus sine 45 degrees, sine 60 degrees. One thing you're going to notice here is that since we're writing everything in terms of things we already know about on the unit circle, the only values we're ending up using are pretty much the 1/2, square root of 2 over 2, square root of 3 over 2, right? All of our answers are going to look very similar. They might have a different sign in between them, a plus or minus, but we're using the same values to get there. So we're not using we're not going to have a variety of numerical answers here, numbers that we're using, okay? Not a variety of numbers involved on this part here. Okay, so cosine of 45 degrees is square root of 2 over 2. Cosine of 60 degrees, 1/2. Sine of 45 degrees, sine of 60 degrees.
Square root of 3 over 2.
So this time I'm getting square root of 2 over 4 minus square root of 6 over 4, square root of 2 minus square root of 6 over 4. That would be my exact value for the cosine of 105 degrees. So we're practicing using this sum and difference formula, and then we're going to see how to use it for some other things later on, today's not Thursday. Today is Thursday. So we'll see how to use it on Tuesday. I've got my days all screwed up now because of the break here. Does anybody have a question on plugging these in? Go ahead.
On that one, could you use 135 and 30?
You could have used 135 and 30. Yes, 135 degrees minus 30 degrees. That is correct. Now, your answers may come out looking a little bit different. I don't think so. I think it's going to be pretty close to the same thing here. Whenever you work it out, though, they're going to equal the same. Okay? Any other questions there? here's what I want you to practice with, okay? We got two sections here that we're practicing with on 7.4 and 7.5. Let me write 7.5 first because I'm already over here on this page 481. So far on that part, I only want you to look at, let's try 11 through 19. Odd, try those. And one of those is a tangent, which I didn't get to do an example of. But then over on page 469, no, actually 470, with the identities. I want you to try establishing these identities. And I know some of these will be different from each other, but try these on 19 through, see how you can do with 19 through 61 odd, as many of those as you can, okay? Practice makes perfect, and it helps get those identities in your head. Any other questions today? Now, you all have a homework assignment to turn in, so please turn that in. You all can give it to David over there in Kingsport. You all can lay it back here on the back desk as you go out in this classroom, and get those in to me, okay? Have a great day, and I'll see you then on Tuesday.